Okay, so when we left off last time, we were looking at different types of scans that we can do. So just a quick review, we had our A scan, and this is what we're going to perform. This is what the equipment we have is for. And then here I had an A scan versus a B scan. So A scan on the left, a B scan of the same part on the right here. And so notice on the A scan, it can give us kind of the depth each part, right? From the left to the right gives us our depth. The B scan gives us depth, but it can also give us the width of each flaw or each feature. But we have to have something called an encoder in order to do that. So an encoder is like a little wheel or a thing you attach to the side of your probe that allows it to track how far you've moved that probe. Then we looked at C-scan, which is now we get a 2D array. And this is what people, when you say ultrasound, are probably most familiar with. Typically what you see with medical ultrasounds are a C-scan, a two-dimensional kind of image, so to speak, of the of whatever it is that you are scanning. And so there's a couple different ways it can be accomplished. One is to have an array probe that's two-dimensional. So it's a bunch of ultrasonic sensors all kind of in a panel, right? And it's going to be able to tell which sensor, which of the sensors are doing it. The ones that are used for like medical, particularly for maternity stuff for babies, right? You see they're kind of linear. They actually they're able to sweep the beam back and forth. So they kind of create a fan-shaped beam that sweeps back and forth. And we do have those for industrial X-ray or industrial ultrasound as well. The other way to do it is to take a probe and move it across a two-dimensional plane, which in that case you have again an encoder, a little set of wheels. It's kind of like how many of you remember like old school mice where they had the ball in them, not the little laser ones, but the ball ran on a wheel that measured left, right, and then another one forward and back. They'd get dust and dirt buildup. They were really gross after a while, especially the ones in like schools and things. Or my brother's desk. But you would move this thing across. It would track the location of the probe as you move it, and it's going to give you a two-dimensional scan of where those flaws are inside the part. And then the most detailed now is what we call a D-scan, and that is basically taking C-scan technology but then being able to take this image and instead of just showing it flat on a two-dimensional plane, we're able to kind of create a visual 3D model of it. And in fact, there's technology, now with like 3D printing and stuff, they can actually take these and feed them into like a 3D printer, and you can actually perform an ultrasonic scan, a D scan, and then create a 3D model using that. They're looking at ways of doing that, or even manufacturing things like blades and other stuff using metal deposit. And so it's kind of a way to be able to, one way is to kind of reverse engineer products and things like that. So here are some of those, just kind of how that phased array works. So our normal beam at the top where we move our part across, and then we can have a couple different types of phased array, sector scanning, where the transducer kind of creates like a cone. It's able to steer the beam mechanically, so you can physically move the probe. It actually moves inside of there. And most of what you're going to have today now is a matrix array transducer that can do electrical scanning, or it uses by having what's phased array, you can actually steer the beam with different sensors by changing like the power in different sensors. And so this is where you no longer have to even necessarily move, that transducer. It can be in one spot and it can scan a three-dimensional area. And it works similar to, if anyone's familiar with like communications technology, in the radio spectrum, things like the fixed dishes, like Starlink dishes, for instance, they used a phased array radio where they can steer the beam kind of the same way. The new dishes don't have to actually move. They just point in a general direction, and you can steer the beam. And that's what this is doing with sonic waves instead of radio waves. And so we're able to do that to create those 2D and 3D, three-dimensional images that can be used. So now we're going to kind of go through what you're going to do in lab. Rather than going through the slide here, I'm going to show you the slides here. But these are online if you want to see them. But what I'm going to actually do is pull up the tester here in a second and kind of show you these different things. But a few things to see. On the left side of the screen, you'll see the initial pulse where the sound is going into the material. When we're in a non-flawed area, we're going to see a back wall echo. Okay. And then if you go the range at the bottom, and we can set our range. And then we can set things like frequency, gain, which is how sensitive it is. And then when we go across something like a defect, we'll see two things happen. So first of all, you can see the amount of energy of the back wall is reduced, right? Because part of the echo is going off the back wall. But now we have a portion of the echo is going off of a defect. So that energy is kind of split between those two pulses. And then you can also see that the defect, time or distance, this bottom scale can represent either. It can represent time or distance. It shows that that defect is somewhere between the front wall at the left and the back wall echo here, the back wall on the right. Okay? But in order to be able to measure that properly and do that, we have to actually calibrate our device. And that's what things like this step block that I have here that I'll show you today. Or we can do something called a primary secondary echo method if we don't have multiple thicknesses. We can do it using that. And what I'm going to do, I'll quickly demonstrate them here. When you're in lab, or if you want to review this more, I've created a couple videos covering this that you can watch, and a lot of students find it helpful to pull it up while you're actually performing ultrasound in order to kind of work through the steps of performing calibration. Because ultimately, for the practical final exam, you're going to need to perform a calibration of the device and identify a flaw in a part. And it may be that you have a stepped block, or it may be that you have to do primary secondary echo where you don't have two steps to compare. Okay? So I'm going to, instead of showing these, I'm going to switch to our actual tester here. And try to kind of put these side by side. So, nope. So our actual tester looks something like this. Okay. And I'm going to actually, uh-oh, did we lose our connection? Oh, there it goes. Just made it smaller. Okay, so that's our actual tester. And then what I'm going to do, I really don't want to change my screen here. Make it a little bit smaller. Too small. Make it a little bigger. And then I'm going to try to kind of keep my screen. I'll kind of work my part down here on the camera. So that's, oh, I got to flip my, that's about right there. So that's where I'm going to put my piece. Okay. So that's that step block I was talking about. If I turn it on the side, you can see it's got steps on it. Sorry, the focus isn't the greatest. It's kind of a fixed focus camera. It's not really designed to be this close. I got to come up with a better camera solution here. I'm working on it. But this has steps of, quite readable on there, but we have steps of 100 thousandths, 200, 300, 400, and 500 thousandths, or 0.1, 0.2, 0.3, 0.4, and 0.5 inches thick. So we're going to get different thicknesses with each of those as we go across our part. Now our tester here, a couple things. I've got it turned on. I'm going to leave it on because right now I've got it streaming to my computer. If I shut it off, we'll lose that. I'll have to go through the whole setup process again. But normally to turn it on, there's an on button in the middle at the bottom. When we're done, we want to shut it off. Don't use the button. Use the red button right here.